Yeah, okay, hi. Today I'd like to present you my recent work based on my thesis. It's named on the distribution of the last exit time over a slowly growing boundary for Gaussian process. Basically, the question is the following. So imagine you have a Gaussian process. As we've already, I guess, seen several times here, it's basically a distribution on the space of functions. So you take some function randomly. And I consider not any Gaussian distribution, but a stationary one. It means that you can shift your function in time and the distribution doesn't change. So you can see on the picture an example of such a function. Also, we fix the following. So we fix the expectation function of our process. As we've seen, it can be defined by its expectation function and by its covariance. And we fix that its expectation is 0. So it doesn't matter. And we fix it as 0. That's why the example goes like around 0, because it has to return back eventually. And for of a Gaussian process, yeah, okay, no problem. So I can write it on a blackboard if you. So we consider the following. So you take a y of t. In my case, t is just from R. So it's a process. If and only if for any finite set like t1, etc., tn, the vector y taken in these points is Gaussian. Yes. Yeah. Actually, it's okay. I will. In this case, I'll say that it's like family. So it's family of random variables y t indexed by t on R. They are random variables on some probability. Okay, but you can treat it not as a family of random variables. It's a natural, like in this subject of random processes. You can consider them as a variable that you take at some point, and like they live on a common space. That's why you can treat different ones at the same time. But also you can take like if you take a particular omega, right? So if you fix omega from our space and you take y t of omega, it's a trajectory. So you take it's a function. Yeah. Like in general definition, no, but I consider only a continuous function. And well, what do you consider? I mean, okay. So in okay, so when we have this definition, you can basically change a variable at the set of zero measure, and it doesn't change the distribution. That's why it's not that obvious how to have, so you can handle different processes, but they have the same distribution. That's why if you have one trajectory, you have a particular function, but basically I can change it at this point and can change it at this point, and it doesn't change the process as a whole. That's why, and there is a theorem that says that we can fix under some restrictions. Definitely for Gaussian processes under restrictions I consider, you can fix the type of trajectory. So you can change something and you get that with probability 1, all the trajectories are. Okay, I can say that's why maybe it's better to say it this way. It's not a family. Okay, no problem. Precise definition is as follows. So we have some probability space omega, and you take y. It's from omega times t is time. In my case, t is r. So it's omega of derivatives in r. So it just you have omega here and t here, and you get y of omega t, right? And so basically you get a random function because you have your probability space, right?
No need to explain this.
Okay.
No, this is a definition, but yes, it is okay. But then also the speaker tells that the relative continuous is wrong because I can
Some Gaussian, okay. There is a definition of integer numbers, some of them are positive. There is a definition of Gaussian processes, some of them are almost true continuous.
Yes.
Some numbers are positive, some Gaussian processes are almost true continuous.
But I mean, you can just add it in our definition in a way that I consider. So it's a random function. It's a random function, and we consider like the space of continuous function. So,
what do you mean you consider? So your object is what is the object?
well, you can define like a Gaussian process.
A restriction of this function y.
Yes. You take a random function from some space, and I'd like to take a random function from space of continuous function.
So the author considers specific type of a Gaussian process of which the trajectories are continuous. That is all, and that is basically determined, I think, by the covariance of this Gaussian for finite Gaussian measure.
All the difference cannot be continuous. Yes, we could get some restrictions. Probably you take just some restriction of this function y. Just understand.
Yeah, I have some. So basically, as in finite dimensional case, this process is defined in the definition is defined by two things. Like its expectation function.
Could you answer yes or no?
Do I have some restrictions on y? Yes, I have. It has to have continuous trajectory.
I mean, restriction of a function. You take a set, a subset, and restrict your function to a certain subset. In this sense, is it true? Is it true that
Yeah, sorry, could you like explain your question a bit because I don't get.
Maybe again we like after the talk, because we like have limited time and stuff like this.
It's fine. You just okay, take it in the following way. So we have functions, yes, and consider only continuous functions.
So we remove all possible terms on the end of t from your space, such that the resulting function is discontinuous. Is that
No. So we take all omega and t. We just so when we take a random function, we consider only continuous function. Yeah.
Do you understand correctly that Brownian motion is an example?
Yeah, of course.
Of continuous Gaussian program.
Yes.
Yes. No. Because as written, it is not true. I can give you a sample only for which this will be.
Yeah, I mean, you're
Because the
right.
definition is wrong, probably, so it's wrong now. I'm asking for correction. Sorry for waiting too long.
Okay, I see what you're talking about, I guess. Okay, so you, I'm not considered. Yeah, okay, okay. That's fine.
Another question.
Yeah, you can.
The first line of the slide is actually positive on the floor.
Sorry, in the first.
Line of the slide should be really close, not equal. So why is it equal to 7?
It should, because since we have continuous trajectories, we know that like this set is closed, and with probability 1 it is bounded, because it can't go like for a type of boundaries we consider, it doesn't grow too much. Okay, so the question. Okay, thank you for the question. I guess that like you can treat it as consider a Brownian motion as an example. It's not an example of a stationary process, but there is actually a bit further an example of a stationary process. It's called, I will show it a bit later. Okay, so imagine you have a stationary centered Gaussian process. So its distribution can be shifted, so it's shift invariant, and its expectation function is just 0. Then we consider the following question. We take some shape of the boundary. Basically, we're interested in two types of shapes, so an exponential one, like exponential of t to the power q, where q is restricted to be from 0 to 1, and polynomial one, like t to some power d, where d is greater than 0. And we introduce a scaling parameter epsilon and consider a boundary, which is epsilon times f of t. So f defines its shape, and via scaling parameter epsilon, we can like scale it in y coordinate. And then we consider the last moment that our process hits this line. So it goes like in the picture, and from some point it goes under this boundary with probability 1, basically because, well, it depends on growth rate of f, but if f grows faster than logarithm to the power 1/2, it's true. And we are interested in the like asymptotic distribution of this moment. Basically, this question appeared in the recent work of Mikhail Lifshits, contributed to one physical model, but and well, after a bit of studying, it was clear that there is no result in this field. But actually, the question like that is considered, and it's basically considered in the following setting. So imagine I will draw it in a bit different way. So imagine that you have a process defined like that. You have some initial condition u is just a number, plus your okay, yeah, I see. So you have u plus your epsilon times f of t and minus y of t. And this process is called a risk process because it
allows us to model a simple case of a company balance that has, so in this particular case, U is just a starting balance of a company. The following function, deterministic one, is its defined income, and Y is some stochastic additive. So maybe some like some events happen that we can't predict, and we don't know exactly the money that we have to spend or maybe receive from these events. And in this setting, we get that the process looks like that on the picture, and the time we consider is basically the last time that the process goes below zero. That is the last time the company needs some funding, and after this moment, it's self-sustainable. That's why this question is well handled. In some cases, there are a lot of force contributed to it, but basically what differs them from this particular result is that the process which is considered is like almost all the time has stationary increments, for instance, like a Brownian motion. And the trend parameter, so this function, deterministic ones, is fixed, while we consider the case that this function goes to zero in some sense. Okay, so, and well, the main result is the following. You can get the limit theorem for the distribution of this moment under like two conditions. And conditions, so you can see them on screen, but I'll explain them a bit. So both the conditions are on the covariance function of our process. And basically the first one handles its asymptotic behavior around zero. It says that it has some Hölder asymptotic, like it has to be regular with, so you can see the formula, but basically it's a Hölder assumption on it. And the second one treats its asymptotic behavior at infinity, and it says that it has to decay not slower, well, faster than 1 over logarithm of them. Under these two assumptions and with some constants, particularly C, you can see on the screen, it is defined via Q, alpha, and well pi. H alpha is a specific constant. It's named Pican's constant. You can just like, well, it's a specific constant, but if you'd like, you can Google it. It appears in some different works. I will show why it is here on the next slide. And you can write the normalizing constants A epsilon and B epsilon. They are written in the work, just the formula is well big enough. That's why I'd like to show it maybe later, such that, well, after scaling the moment t, so we shift it by A and divide by B, we get the convergence in a distribution of this random variable to a double exponential distribution. Yes, okay, so I'd like to add also a note that basically the distribution, this double exponential distribution, it seems like it depends on C, but the dependence is really small because you can, so you can put it as a logarithm in the exponent, as an exponent. And this is basically a shift of R. So all of the distribution, they differ just by shifting of your axis. Okay. Okay, but while we see the conditions, I'd like to emphasize a bit that well, they are quite basic, because when you have a Gaussian process, it is often just defined by its covariance function. And also, well, it's not that hard to check the assumptions on it, even if it's not defined, but it's just numerical, because you can consider like, well, you can find a numerical approximation of a covariance function. That's why it's not hard to check these conditions. And it was maybe the biggest tackle, because while proving the result in the first work that the question appeared, the condition, so it appeared for a particular process and it was handled there, but the solution heavily depended on a really strong assumption. And well, the hardest part was to lighten this assumption and to get this one. Basically, okay, so the of which one? Sorry. Yeah, because I can, because I have them written, like it's just okay. So yes, I know the exact form of the constants. And V is just variance of your process, because as you see in the definition, epsilon is a scaling parameter, right? So we scale y coordinate, and well, you can also scale just the process. You can divide it by v and get that it's so if you consider t equals 0, you get that variance of y0 is just v squared. So it's not an important parameter, it's just in the definition. But the first thing we do, we divide by v, because you can scale not only the boundary, but the process itself. No, I don't, because we consider like the right hand side of this event. So the boundary, if you want to continue the boundary to the left side, you get that it's higher than it, obviously. Okay. Yeah, it's really weak, and basically it even has a name. It's named a Berman assumption, and we like didn't know it before studying this model, but it appeared that it occurs in different results on limit theorem for maximum of of a sequence of random variables, and it's like the weakest assumption one can get in this results. So we think that it's the weakest one here also. Yes, it is true. So basically there is a okay, so it is true for exponential for these two types of f, but it's actually true for so I have a bit harder to explain assumptions on f, which allow you to tackle different function you want. I just wanted to tackle this too, because it's like a natural example. Because basically you can't consider exponential, you can consider just e to the power t for a reason I can explain, and you can't consider logarithmic function for another reason I can explain. That's why, well, these two remain. Okay. Yes, I mean this two. Okay. So the simplest example is just the most, I guess, popular stationary Gaussian process is an Ornstein-Uhlenbeck process, and it can be so it can be treated in different ways. It's like I guess that everything is known about it, but basically its definition is the following: it's a Gaussian process with covariance function e to the power minus model absolute value of t minus s divided by 2. And also we consider the simplest example of the boundary just because it allows to write these constants in a simple way. And then you just can take these two constants, like square root of -2 logarithm of epsilon divided by epsilon and 1 over epsilon times square root of -2 logarithm of epsilon, and you get the result of the theorem. So you know that this moment, its first term of its asymptotic is a epsilon, and the second one is stochastic. It's b epsilon times Gumbel distribution. That it's the same distribution, just has a name, with the constant c, just 8p to the power -1/2. And here you can see a picture of a probability density of Gumbel distribution. So basically in the theorem, it's the same because as I mentioned, you can shift it. So the constant only corresponds to shifting of this distribution, but it looks the same. Yes, okay, so this is the result, and well, I can show you the the conditions on the function, but I guess it's not the most important part. I'd like to share a little bit of technique we used. It's basically two things. So the first one, and basically we used two famous results in for Gaussian process, and that's why we get two conditions on our process. The first one is Pekan's lemma. It's a bit huge to consider, but basically it's the following. So imagine you have a Gaussian process, and you know that its covariance function is in a sense regular around 0. So you know that different values of your process, you know how they correlate if they are close, and that's why basically you can think that they are continuous, because you know that they have to be, their values have to be really close when t goes to 0. And then you also can handle so the Pekan's lemma shows you that you can find asymptotically the distribution of a maximum of your process over an interval. So because you know that if this interval is, well, if it's quite small, then you know that the process doesn't change a lot, and you can you can find its maximum in a sense. But so that's a famous result in this field, particular one, and it allows us to consider not the process in general, but to divide it into different parts and to handle it like a sequence of random variables, which is a lot easier. Yeah, but this step was quite clear. And the surprising part is the second step. So since you get, so I can draw maybe a picture. So, okay. The first part is following. So you have your
process somewhere here, and we have our boundary, which is basically I'll draw it as a linear function, but we've seen, and you can approximate this function just by this linear, not linear, but by stairs, and then, well, if your process intersects this boundary, it also has to intersect the stairs, and you are interested now. So the event for intersecting the boundary is the question whether maximum of your process over this interval is bigger than this value or not. And well, the Wittgen's lemma allows us to, in a sense, calculate this distribution of maxima over this interval. That's why you can omit this process and just consider a sequence of random variables. But then the problem is that they are highly dependent, because, well, around this point, for instance, your process, so it's close here, it's close to this point, and here it's also close to this point. That's why these events are dependent. And, well, if you have a sequence of really dependent random variables, you can say a lot about them. And that's where the second idea goes into the place. We not only divide it with the intervals, but we also consider like this separating smaller intervals. So we just we know, like, for a reason that all the asymptotic behavior of this event, it's not like everywhere. We can just throw out some small intervals, and we do it basically, and they allow us to separate these events. So we consider these intervals, they are important ones, and the rest, they are just separated ones. And now our intervals are a little bit separated, and we know that since they are separated, their covariance now is bounded by the second condition. So I hope you remember that it was about covariance. So it's this. So it's enough to bound covariance. We know that their covariance on the different intervals is bounded. And now you can apply the second result.
And well, the second result is the following. So there is a Slepian inequality, and it's also used, well, only for Gaussian random variables, but it basically, I will maybe explain it in the simplest case. So imagine you have to
just run just Gaussian random vectors u and v. So it's u1, etc. un, and v1, etc. vn. Two Gaussian centered random vectors. And you know that, well, there, you know that their variances are the same, so you expectation of your square is the same as same one for v, and you have an inequality for their, so basically a scalar product. So if you take the variance of u dot and u j, you get, so it's smaller than covariance of the same one of v. And then, well, for some reason, I actually don't know why, but you get that this vector hits like its maximum hits the boundary with higher probability than this one. So probability of maximum of E to be bigger than something is higher than probability of maximum of E to be higher than some number. So for any number of yeah, that's why I don't know why it happens. And, no, it's the same way as it's written there. So, yes, I don't know why, because it seems like these vectors, they were more close to each other, but for some reason they keep this event. Yes, maybe. Okay, so that's, for now it's a question from me too. I just like know. So I was told about this inequality and I found it in the book, and it's true, but well, it's difficult to repeat it.
And well, you can like use some basic properties to derive a more like suitable statement for us. It's more general, but basically it's the same. And then it helps by some trick, but you can clearly see that well, there is an inequality for covariance here, and we also have some inequality for covariance, and that allows us not to just consider the sequence of random variables, but to make them independent in a sense. And then we treat a sequence of independent random variables like the simplest case, and you can derive the result in this case. That's why you get this double exponential distribution. Well, that's like the two main ideas of the solution. Because if you check it for a sequence of independent random variables, you get double exponential. But it's basically like some asymptotic stuff. But there is a theorem that states that if you consider any maximum of a sequence of independent random variables, you get one of three distributions, and one of them is double exponential. So it's not a surprise that you get. But it's just you have to count it. So you write down what the probability is, and you get that you find some asymptotic of some. Yes.
The argument with the stairs is give you only one part.
Yeah, we can also like have stairs from the other side. So yeah. Yeah, okay, so that's all that I wanted to share. I can just show you the formula for A epsilon and B epsilon, but it's quite not so cute. The first one is that basically I lied a bit, and I can treat not only these two types of boundaries, I have some technical assumptions on the boundary. So you can see them here. So it has to be like, so I don't want even to read it because it's not like, there is no, so it's just because I can count some integral asymptotic in the case when the function is like that. But yeah, so the two cases I considered, they follow these assumptions. And then under these assumptions, you can basically define a few constants. It's gamma. Gamma is defined via the inverse function of f. as follows, and you can define tau. Tau is, well, in a sense, also defined by the inverse function of f, and there is an explicit formula, if you can say so, when you use an inverse function of f for a epsilon and b epsilon. But you can find, well, if you take a particular boundary, for instance, a polynomial one, you can, well, write down all the results and you get the exact formula for a epsilon and b epsilon. You can find them here. So yes. Sorry, wait a second. Sorry, yeah. Okay, so yes, it goes to infinity. Your question? Yeah. Sorry, what do you mean up to something? So I have, maybe I skipped too fast. I have this assumption that f is like fine. So it's okay, just next week. Yeah, you can take any gamma depending on epsilon such that its square is, yes, it's important basically. So I could just write so without that it's not, yeah, okay. And yeah, well, you can find the exact formulas for A and B, and even in the exponential case, you can find them too. Yeah, so that's all. Okay, maybe some questions?
Does it exist any initial scaling in function f and say it is higher? Say f is function f. Whether I understand that since it has not Brownian motion, but there are also other.
No, I guess it's basically here in this constant that it isn't so. So if you mean like a simple scaling, just multiplied by constant.
No, no. Yeah, it has to be complicated.
So you mean
replace f by I don't know, f squared or.
Yeah. Okay, I see. I don't know.
No, because it's might be like.
Yeah. Yes.
But certainly you have to change time.
Yeah, I actually, so yeah, I can say that your question, it is important in a sense. So when I tried to handle the logarithmic growth of f, which is basically to change like f in a sense, you can take like a polynomial one and take logarithm. Then you also have, so this form of the scaling is not true, and you have to write here logarithm of t. So if you want to handle, for instance, just logarithm, you also have to take logarithm of t. But the problem is that, well, it's hard then to work with asymptotic results. So they are really technical, and even after such a simple transformation, they doesn't sum up in a sense. Yeah, they are complicated in a sense because, well, well, basically what they represent is you can write, you have this time t, and you start to write its asymptotic in epsilon, and you get that in this formula, you get that it looks like that. So the first several terms are deterministic. like before the accuracy of 1 over well something, and then appears at the same accuracy a stochastic term, which is basically b epsilon times Gumbel distribution. And well, if you try it explicitly for a particular boundary, you get that it's not like one term, it's several terms. So you write several terms, you get to some accuracy, and then you get a stochastic term. Well, in all the statements, basically, so Pican's lemma and Slepian inequality only work for stationary process. So the statement isn't correct, but the thing is that in the field there are a lot of results for, like for instance, for Brownian motion. So you can easily write any such statement for Brownian motion, and if you are interested in the asymptotic behavior of which we considered, you can just take this parameter going to 0 in the results that are famous. I mean, so it's not, so I don't know the solution for not stationary case, but it is better studied in the field.
Next.
Well, since it was my thesis and I finished it, I guess my next step is to do something else. But if anyone wonders, I could recommend to consider a field instead of just a process, because, well, I think it's basically the same. Well, the result is, the proof is technical. So you can see huge formulas, and it's not like they appear in huge work.
So then I ask another question.
Yeah.
Like another potential. There are a lot of similarities between random processes that could appear.
Yes.
Especially here because you allow some relation even longer.
Yeah, and also I consider like stationary case, so it's basically invariant transformation.
Yeah. So a lot of, and because typical in the dynamic never have total.
Yeah.
Exponential game not better.
Oh, that's an interesting question. I didn't think about it, so I don't know, but
And the analysis, so am I working for from the function that you then so over means wait. The perspective is that there exists a yeah, the question. Yeah, the last. Yeah, but usually those problems do.
yeah, I see. So yes, but that's also a great question. Thank you.